Okay, now we get down to it. So, avian, which means bird, and human flu viruses actually bind to different types of sialic acid. And it seems like sialic acid should just be a chemical, and it is. But it turns out there's two ways you can hook it up. You can hook it up by the front end, or you can hook it up by the back end. So in birds, we hook it up by the front end. So it's an alpha 2 3 linkage. And the next slide will show you in chemical terms what that means. But what it means in a nutshell is that we number the carbons in this molecule. And so we're linking carbon number 2 to carbon number 3 in an alpha 2 3 linkage, and there's going to be an oxygen in between those two. So that's the idea. The other way, and so that's what birds primarily do, that's what they have in their lungs. The other way to do it is with an alpha 2 6 linkage, and so carbon 2 hooked to carbon 6 again via an oxygen. And yeah, that's just another way to link these things together, and that's what humans tend to do. Now, the other neat thing is that pigs have a nice mixture of alpha 2 3 and alpha 2 6 sialic acid throughout their lungs. So that's why pigs are ideal mixing vessels for making new viruses. Because the bird virus can grow in pigs already, or it can enter at least, and the human viruses can also grow in pigs. And the evidence there is that they are still carrying our good old 1918 flu, preserving it for everybody. Yeah. Okay, here's a nice little picture of what those sialic acids look like. So a single sialic acid molecule is shown up in the upper left. It's that sort of ring in the chair conformation with a little O in the ring part of it. And you can see it's got some little branchy side chains hanging off. So, and then lactose is going to be a disaccharide. And so we will add on the sialic acid to a lactose, but we're going to add it on in different ways. So way number one is that we can add it on just like you see in avian, and so that is going to be the sialic acid alpha 2 3 lactose. So we just abbreviate that as alpha 2 3. And they've written it as a regular A there, but you should probably write it as the little Greek A, which kind of looks like a little short, fat fish. And then the other way that you can link it up is the alpha 2 6 linkage. And so you can see it's actually joined to a different part of the molecule. We've actually turned that lactose molecule upside down. You see how the oxygen was on the bottom, now it's up on the top. So we flipped this whole thing over and fine, attached it to a different little side chain coming off a different carbon. So it's one of those two things at the bottom that look like a pair of legs on the lactose part of the avian, or look like two legs sticking up in the air on the lactose all by itself. You see what I'm talking about? It's the two OHs at the top left side of the lactose molecule, which is top right on here. So anyway, yeah, those are the two ways you can hook up a sialic acid, which is the thing at the left, to a lactose, which is part of the glycan chain, the sugar chain, and that's the difference. So avian hemagglutinins will recognize the alpha 2 3 preferentially, and human influenzas, hemagglutinins, will recognize the alpha 2 6. But it turns out that when you put it through something like a ferret, you can change the avian one, and so it'll then switch from recognizing just an alpha 2 3, and it'll go over to recognizing alpha 2 6. And so that's why running these viruses through ferrets is potentially dangerous if they start out as avian viruses anyway. All right, so yeah, why are the receptors different for human and flu viruses, avian flu viruses? Well, the short answer is that the site of replication differs. So flu viruses are enteric, meaning they go into the intestines and they cause diarrhea in birds. Now, it's a lethal diarrhea. They die of it, so that's extra terrible, I guess. But it's quite different from the site where they grow in humans, which is going to be in the upper respiratory tract. So the top half of the lungs and the airways are going to be infected in humans. Yeah. So it's just a different receptor in different places, and that's the big difference. All right. So the respiratory environment actually looks something like this. So you're going to have these mucosal membranes. This is going to be the surface on the inside of your nose. That's the nasal mucosa. And so there you can see the blue are little nuclei. So those are little blue circles. And then you've got a mixture of alpha 2,6 on the surface and alpha 2,3, mostly on the interior. So most of what is showing in your nose is going to be alpha 2,6, which is why human flu viruses are going to bind alpha 2,6. And so then if they get past the nasal mucosa and they make it to the paranasal sinus, like your sinuses, the thing that gives you headaches, it's hooked up to your nose, then look at that. Those are just solid alpha 2,6. So we think this is where the flu virus will start to grow. And then if you get into the bronchi, in one bronchus, look at the surface there, bright green, which means alpha 2,6 once again. So we are alpha 2,6 all over the place at the start of our respiratory tract. But once you get down into the lung, there's a mixture. So in the lung photo there, you can see the little holes. That's the alveoli where the air would go. And you see a mixture. You see it's mostly alpha 2,6, but there's a bit of alpha 2,3. So the big difference between us and pigs is that pigs will also have alpha 2,3 sialic acid much more abundantly up in their nasal mucosa and paranasal sinus and bronchus. We both have roughly equivalent amounts once we get down into the lung. And once you get toward the bottom of the lung, humans have a lot more alpha 2,3. So you can get lower respiratory infections with avian flu viruses, which are real bad. Okay, so yeah, human H3N2 or H1N1 tends to hit the nasal cavities, the sinus, and the bronchi. It doesn't tend to go much into the lower respiratory tract. It's going to stay up near the top. Because that's where all the alpha 2,6 is, and human viruses just go from alpha 2,6 to alpha 2,6. They don't have any way to use alpha 2,3, and so all the bottom of the lungs are kind of dead to them. But avian H5N1, so it's harder to get because you have to get it past all that alpha 2,6 without it binding to anything and getting stuck or stuck on mucus. But if it gets all the way down into the bottom of your lungs, then you can get a really bad infection, and then it gets really hard to get out, and it causes a disease similar to what SARS causes. So most often H5 deaths are in children, and we think part of the idea is that they have a shorter trachea. So there's just less passageway for the virus to go until it gets to the bottom of the lungs, and so it's easier for the virus to get there. So yeah, that's terrible. Okay, so what's the inside of a respiratory environment look like? Well, you've got a couple different kinds of cells. So you're going to have a mucus layer over the top, and that's going to be this sort of grayish layer on the left or this sort of purplish layer on the right at the top. And you're going to have all these ciliated cells. Now, the ciliated cells are making an epithelium, and these are in the airways, by the way. And then the cells in between are going to be non-ciliated, and they are going to secrete the mucus. So that's how everything sticks together and works. So if you wanted to look, this is looking for where is the alpha 2,6 sialic acid and where is the alpha 2,3 sialic acid. So the tubulin is showing you where the cilia are, because tubulin is running down the center of each of those cilia. So all the little red tufts, or if you're colorblind, the things that are standing up a little bit higher in these images, those are the ciliated cells. And the green in each image is going to be staining with a lectin, which is a sugar-binding protein. But for this, let's just say it is showing you where all the sialic acids are. So the one on the left, we're showing where the alpha 2,6 sialic acid is, and it's all on the cells that don't have cilia. And on the right, we're showing you where the alpha 2,3 sialic acid is, and it's all on the cells that do have cilia. So the avian influenza will infect those cells that do have cilia if it gets into a person, and the regular human influenza will infect those cells in between the ones that have cilia if it's a person. Okay. And so, not surprisingly, if you put in the human virus, it will go in and it will infect predominantly cells that don't have cilia on them. And if you put in the avian viruses, so influenza A duck UK or A duck Singapore, like shown here, it will almost exclusively infect cells that do have those cilia on them because they have the alpha 2/3 and the regular old A Victoria, which is one of the vaccine strains that we use. That's going to infect all the non ciliated cells. So that's exactly what it appears to be doing. So there are just a couple amino acid residues in the hemagglutinin, and changing those can change the preference for sialic acid linkage. So these are the amino acids shown here, and specific changes in these amino acids, sometimes even a single change or a set of two changes, can cause the virus to switch from binding alpha 2/6 to binding alpha 2/3, or vice versa. So it's kind of neat. Oh, and that was done by James Stevens. Yeah, he's a friend of mine. He worked on SARS with me back in the day. Here on this slide, you can see that HA mutants. So if you pick up the right mutations, like through antigenic drift, those can actually switch receptor preference. So if they make the right mutations, then all of a sudden they are able to infect the other cells they couldn't infect before. So if you had me for biology 2 fairly recently, this is like the Lenski experiment. And so that was the experiment with E. coli evolution, where they put in a lot of citrate and a little bit of glucose. And they put in these E. coli. They could only use the glucose unless they could figure out how to genetically switch on a citrate transporter that would let them take in the citrate. And if they could, there was just this extra energy that was there for them. And so they let these things go for years and years and years, and then finally, one of them makes the right combination of mutations. It's actually a duplicated part of its genome, and it can get access to that citrate, and it just grows like mad. It kind of wipes out all the other viruses that are glucose only. So there's an advantage for the flu virus once it gets into a person if it can switch over. So it's going to have the best time infecting a person if it's alpha 2/6 binding, but if it's able to switch over to alpha 2/3 binding once it's in there, then those viruses that switch can get a little extra place to grow and do a little bit better. So, yeah, we think that this can happen and sometimes does happen in the real world, which is, yeah, probably not what you want to hear, right? Let's see. And so, pandemic 2009 H1N1 definitely binds to non-ciliated cells. Sorry, so these are the ones with the alpha 2/6, and you can see right there. So the green is standing for hemagglutinins, which is viruses that have stuck to these cells, and you can see there's little patches of green and that don't have any cilia, and then you got the red, which is again standing for tubulin, and that's marking where the cilia are. And so those cells with cilia don't have any virus, and the cells next to them that don't have any cilia have tons of virus. Doesn't really matter as far as the virus is concerned which one it infects. As long as it gets into a cell, it's happy. But that is what H1N1 is trying to do to you. It's trying to get to those non-ciliated cells with alpha 2/6 sialic acid. Have I said alpha 2/3 and alpha 2/6 enough times now? I hope I have. I think I'm not going to say them anymore, but make sure you've got good notes once again. You're going to be taking notes as you go through these. Maybe go through on your own after you listen to it, and maybe listen to this twice, like once with me, once with just you looking through the slides for your notes, and then one last time to pick up anything you might have missed. And then you're going to have real good notes, and I like that. All right, last slide in this little section, and this is the next to last section, so we're almost there. Some H5N1 avian strains found in Egypt. Oh, yeah, and these nice migrating Canada geese, look at them, just like we have outside by the pond, are already able to bind human receptors, alpha 2/6, to some degree. So there are strains of H5 out there that are able to bind to human receptors. And one other thing we've learned in recent years is that it takes a couple other changes inside of the virus to make them grow well in a human. So the virus is actually completely adapted to grow in a bird versus a human. One thing about birds is that their body core temperature is a little hotter. It's about 2 degrees Celsius hotter than inside of a human. And so even their lungs are a little hotter, and it turns out their viruses are very well adapted to grow in the heat. And our viruses are very well adapted not to grow in the heat. They grow perfectly well at human body temperature because it's a struggle out there. You got viruses competing with other viruses. And just like the case with the 1918 flu, a new virus comes along, like pandemic H1N1, and it'll drive the old virus, even the Spanish flu virus, to extinction. And yeah, it doesn't take that much. Just it happened over the course of a couple months. We just completely wiped out one virus from the wild and replaced it with another equally terrible virus. Yeah, so there we go. End of the next to last section.